Hello everyone, my name is Luke. This is going to be my submission for the final project in Math 4100 Real Analysis, spring of 2022. So what I'd like to do today is sort of just give a brief overview of proving and defining the real numbers using Cauchy completeness. Of course, up until this point in our class, we've done that with Dedekind cuts. So this is just another way of looking at it, another approach to showing the existence of those numbers. And it's really fascinating and, in my opinion, incredibly intuitive the way that we actually do that. So I'm going to give a quick summary of what that looks like. Unfortunately, we probably won't be able to go through we definitely won't be able to go through proving all of the different field axioms for it, as well as the ordered field axioms with it. But I do want to touch on a couple of them just to show you how they do work and to kind of justify that the rest would work as well. But due to time constraints, we'll just keep it to a couple here. So let's jump right into it. So the basic premise is that the real numbers is the set of all equivalence classes of Cauchy sequences in Q. So this is really, really interesting because you might recall that a Cauchy sequence is the sequence where for some m, as long as you have all n greater than m and all k greater than m, xn minus xk would be less than epsilon. So Cauchy sequences are a really powerful, they hold a lot of strength, they have a lot of great properties to them, and they're going to be really useful in showing the existence of these numbers. So I'd like to kind of get more practical here for a second and talk about what we're really trying to say when we say that R is a set of all equivalence classes. What this means is that every number in R, once again, if it's a number in R that's irrational, then that's easy. We'll show that in just a second. But if it's a number of R that's irrational and cannot be represented by a single rational number, then what we're saying is that that number can be represented as a sequence of rational numbers that converge to it. So taking pi, for example, look at the sequence 3, 3.1, 3.14, 3.141, and so on and so forth. And that infinitely, recall that, so it's infinitely going to keep getting closer and closer to pi. Now, of course, that's not the only sequence that would converge to pi. For example, you might have this sort of oscillating deal right here where it's 4, 5, 3, 3.1, 3.2, 3, 3.1, 3.14, and so on and so forth. It eventually converges. These are clearly two distinct sequences. Not only does it have elements that this doesn't have, it's a different order, which we know is important with sequences. So that's why we bring in the equivalence class aspect to it as well, because we really want to explain and show that, hey, there are multiple sequences that converge to that irrational number or rational that we're trying to define. So that's our equivalence class there. So we want to kind of pay attention to this as well. We're going to say that AN and BN are similar if AN minus BN converges to 0 using this Cauchy completeness. So what I would really like to show as well is what's really powerful about this is that that's actually an equivalence relation, which you'll recall we actually defined an equivalence relation to sort of begin this journey into rational numbers as well as into proving the real numbers with Dedekind cuts. So proving the equivalence relation right off the bat is really important. So we can show that it's reflexive, AN minus AN equals 0, so that's AN minus AN converge to 0. Then if you assume AN is related to B such that AN minus BN converge to 0, then BN minus AN, which is just the negative of AN minus BN, is equivalent to the absolute, so the absolute value of that is equivalent to the absolute value of AN minus BN, which we know is how we're defining that convergence with the Cauchy completeness right there. So thus, since those two are equal, then BN minus AN also goes to 0. So that shows our symmetric property as well. Then if we assume that AN is related to BN, and bn to cn, then we know there is some capital M such that an minus bn is less than epsilon over 2, bn minus cn less than epsilon over 2 when n is greater or equal than m. Then an minus cn can be written as an minus bn plus bn, because that's basically adding 0. Which, recall, since these are rational numbers, that would be our additive inverse for the rationals. And then we have the minus c at the end. We do our triangle inequality, show the epsilon over 2 plus epsilon over 2 equals epsilon when n is greater than m. Plus an minus cn converges 0 for transitivity. So that shows that an minus bn is an equivalence relation. So let's go ahead and move to the next page. So I also wanted to show this because I find this fascinating, because you kind of get to this place where it makes sense. And this is one of those areas. Because if we take some q tilde in the rationals, then q tilde can just be represented as the continuous constant sequence of rational numbers q, right? Those will also converge. And we say those two are similar because that's some reflexiveness, excuse me, I apologize, because q minus q equals 0, converges 0, so it's the same, and then this would converge to q. So that's just kind of showing that you can also represent even just a regular rational number the same way. And then, of course, we also recall that rational numbers have that element of an equivalence class to them, because 1/2 can be equal, or is equal, excuse me, to 2/4. So that's where that equivalent relation is once again proving itself to be important. So anyways, let's get on to some fun stuff here. So we're going to actually define now the structure to use an abstract algebra term here. So we're going to go ahead and go into defining the structure. So let S and T be real numbers such that S can be represented by the equivalence class of the sequence an and T the same of bn. Then we define S plus T to be the equivalence class of an plus bn, and S dot T to be an dot bn. All right, so we want to show there are multiple properties you would have to go through with this, but I think, of course, one of the foundational ones before we move on to the rest, we're showing well-definedness. So I at least want to do that real quick. So suppose that an equals cn and bn equals dn. Then an plus bn minus cn plus dn, we can just move those around, is an minus cn plus bn minus dn. You kind of see where we're going with this. Same trick, right? So then we can use the triangle inequality to go ahead and split that up as such. And then, of course, that can be less than epsilon over 2, which is epsilon for all n greater or equal m. Thus, an plus bn minus cn plus dn converge 0, which means these two are similar. And that implies that that is equivalent to saying that the equivalence class of an plus bn equals the equivalence class of cn plus dn. Thus, we've shown well-definedness in addition, or for plus. Next, we want to do it similarly for dot. You can see, as most people do, I've removed the dot now and just put them together. Hopefully that is okay. So we want to show that given the same conditions before, that an equals cn and bn dn, that an bn is equal to cn dn, which is equivalent to saying an bn minus cn dn converges 0. So what's important is that we can rewrite that by adding 0, right? This bn cn minus bn cn is just 0. So if we go ahead and add that, what's going to end up happening is we can rewrite it as bn times an minus cn and cn times bn minus dn. We put the absolute value bars and use the triangle inequality, we get this. Now, this is really important, and it is a theorem that, if I'm not mistaken, is in the book. But a Cauchy sequence is bound for some n greater or equal m. So this absolute value bn and cn, because these are two Cauchy sequences, those are bound. So we'll just let them be bound by this alpha, and then we can say n minus cn, since it's less than epsilon, is also less than epsilon over 2 alpha. We do that for both of them. Those cancel. That equals epsilon when n greater or equal m. So that means that an bn is equal to Cn dn, as they are similar and converge to 0. Therefore, plus and dot are well defined. Sorry, I apologize if I'm going through this a little bit quickly. And what's interesting is this is barely even scratching the surface of all the different facets that go into showing this. So it's really fascinating. But I wanted to go ahead and jump into some field axiom stuff here to sort of wrap this up. So, of course, we do have, off the top of my head, what is it, 9 or 10 axioms for the fields, and then a couple for the ordered fields. So clearly I won't be able to get through all of those for this, but I wanted to go ahead and define a multiplicative inverse to kind of show you what this looks like with the equivalence classes. So given some non-zero s, that's a real number, we want to show that there exists a t such that s times t equals 1. So there's that, you'll be familiar with that. We define s to be an once again, t to be bn once again, and we want to show that an times bn is equal to the just equivalence class of the sequence 1, which will equal 1. So, given that there is a Cauchy and it does not tend to 0, so we're saying that this is a Cauchy sequence that does not on its own tend to 0, then there exists an n such that for n greater than n, an, which is the individual n, that's the individual a at that n, is not equal to 0. This is also a theorem that I'm not able to prove, but it's a relatively simple proof. But that's effectively saying if this is a Cauchy sequence that does not converge to that 0, then there must be at some point within that sequence that the individual components of the sequence are not 0. So then we can define the bn to be 1 over a to the n when n is greater than that same n that we showed up here, and 0 when little n is less than that, big N. Then we can sort of show that bn is this. So it's going to be 0, 0, 0, 0, 0 up until n, and then after that, so up until that nth term, which it could be between, right? Because n doesn't have to be necessarily a rational, but we try to let it be. But then after that, it's just an, 1 over an, 1 over an, an plus 1, and then that goes on. Then what that means is that an dot bn is going to be an dot 0, right? Which is just going to be equal 0 when our n is less than equal to big N, as we define bn up here. And similarly, that's going to be equal to 1 when our n is greater than that n that we defined up there. So what does that mean? Basically, that means that this sequence is going to be a 0, 0, 0 for some finite many zeros. Then it's going to be equal to 1, like that, for infinitely many. So what that means is that this is equivalent. So we can say that the infinite sequence of just ones minus a and bn, as defined above, is going to be 1 minus 0 when n is less than equal to capital N. And the same thing is going to be equal to 0 when n is greater or equal than. So in other words, an bn is equal to that sequence, which is 1. So Tn, or T equals Bn, is a multiplicative inverse. So that's a very kind of simple way to lay out how you could do it. Similarly, we could define an S and R to say S is positive and let it equal that an where it doesn't converge to 0. Then say that there exists an m such that an is greater than 0 when n is greater than m. We say that s is greater than t for some t and r if s minus t greater than 0, which is another way of saying an minus bn converges to some alpha for alpha greater than 0. So if we also want to define an r that exists here, that equals Cn, we could show that if s is greater than t as an assumption, then s minus t greater than 0, then there exists an m, such that an minus bn is greater than 0, which is equivalent to an being greater than bn when n is greater or equal m. So then you add the Cn to both sides, yielding An plus Cn is greater or equal to Bn plus Cn, because these are rational numbers. And that is a property that does hold for rational numbers, you may recall. So then that means that that same equivalence class is bigger than that, or excuse me, that same sequence is bigger than that for the n greater or equal m, and thus the equivalence class of the sequences are that's greater than that one. So S plus R is greater or equal than T plus R. So yeah, guys, that's just a little bit of a summary walkthrough, and you, of course, can apply that to different parts of the axioms. You can take it further to the Archimedean principle, as well as showing the density of Q and R. You would do that using that same kind of structure that we laid out here. So thank you very much for your time. Hope you have a great night.